Now, when dealing with these wave equations, the second main skill you have to be able to do is you need to be able to look at a characteristic equation for a wave, and you need to be able to figure out the different parameters that are present in this characteristic. So here's the characteristic equation of a pressure wave. It's this mathematical function here. And your goal is to figure out several things about this wave, such as its amplitude, the direction it travels in, its wavelength and frequency, its speed, and whether or not it's longitudinal or transverse. Now, we can do each of these one at a time, and it doesn't really matter what order you go in. So I'm just going to do them in a kind of random order. We're actually going to start at the bottom here, whether or not the wave is longitudinal or transverse. Now, when you take a look at these two waves, what longitudinal or transverse actually means is for longitudinal waves, we are oscillating in the direction that we're traveling in. For transverse waves, we are oscillating in a perpendicular direction to the direction that we're traveling in. Now, if you take a look at this, the direction out front will tell you what direction you are vibrating in, and the thing that is next to the wave number will tell you the direction that you're traveling in. So if you take a look at these two things, you'll notice they're both along the y-axis. And what that means is we are vibrating in the y direction, or along the y-axis, and we're traveling along the y-axis. Because these two are the same, this tells us that our wave is longitudinal. If they were different, we would have a transverse wave. Now, secondly, we need to know the wave's amplitude, or its maximum displacement from equilibrium. In all of the wave equations that we've had, our maximum displacement from equilibrium was right out front, outside of our trigonometric function. So for our amplitude, we'll just have 30 pascals, or 30, whatever thing's out front. And those are the two easiest to do. Now, when we're dealing with the rest of them, we actually need to start examining more in depth our mathematical function. Now, I'm actually going to start with number 3 now, this one here. Its wavelength and its frequency. Now, in this particular equation, we do have two numbers, one associated with our distances and one associated with our times. These are not necessarily our frequency and our wavelength. The 25 meters to the -1 here is actually our wave number k. And the 35 hertz is actually our angular frequency, omega. Now, in order to find the proper wavelength and frequency, you need to know how k and omega are related to wavelength and frequency. Now, for k is always equal to 2 pi divided by lambda. And for omega, or the angular frequency, it's always equal to 2 pi times whatever the normal frequency is. So using this, you can actually rearrange and solve for the wavelength and the frequency just by using math. Because if you know what k is, you can figure out what lambda is, and if you know what omega is, you can figure out what f is. If you rearrange and solve this for lambda, you'll receive 0.25 meters, and for f, the frequency, you'll receive 5.57 hertz. And that's how you would get to number 3. Now, as for number 4, you need to find its speed. Now, there's several ways you can do speed. The easiest way, though, is to simply take the wavelength and multiply it by the frequency. You can also use the wave number and the angular frequency if you like. But if you just take these two and you multiply it together, you'll get about 1.39 meters per second. And those are the 4 main ones that you need to be able to find. The last one here is actually a little bit tricky to deal with, and that's the direction that you're traveling in. Now, how you do this is when you're dealing with directions that you're traveling in order to travel a direction, you're basically looking at a speed. So you need to compare these two terms in green here. Now, I don't know how much you all have done with different functional forms, but the idea is if you take a look at this term, or this pair of terms in the center here, what you can ask yourself is, what happens to my system as I go forward in time? In other words, if time increases, what has to happen to y to keep it the same? So if you take a look at this particular pair of terms here, let's say I want to have them equal to a constant c. Now, if time goes up, in order to keep this thing the same, I need y to go down. What this means is that as time increases, we're decreasing y. So here we're traveling in the negative y direction. Right, so inside here, you'll notice that the y is not a vector. You have to do this comparison between y and the time to figure out what direction you're going in. So what you want to ask yourself is, if I increase time, what do I have to do to my position variable to keep this sum of two terms the same? Now, there is a bit of a shortcut to this. What you want to do is you want to look at the signs of the two terms. So what you'll notice is both the signs of k and of omega are the same. They're both positive. If they're the same, you'll always be traveling in the negative direction. And if they're opposite, one's positive and one's negative, you'll always be traveling in the positive direction of whatever your variable is. And that's a shortcut for figuring out the direction that it travels in. It's actually based off of this functional form by doing a transform as you go forward in time.